Welcome to this recording. Last time in class, we looked at the loss matrix associated with confusing between correct and correct classes and properly assigning classes in a classification task. And here we see again this general loss matrix that specifies that if certain class is correctly captured. Let me also show this here. So here on the diagonal, if a certain object is described as belong to the first class and it actually belongs to the first class, there is a zero loss. And otherwise, if there is a confusion, the loss for this object will be different from zero. A very simple version we saw then was a capturing of the 0-1 loss, where every confusion incurs a loss of 1 and only correct classifications incur a loss of 0. And with this background, we can describe the expected prediction error for classification, which is given here by this formula. This formula describes that we go for all the different objects, all the different x's that we can have in our data distribution, and look at the probability of seeing them to belong to a particular class. And then we look at the classification here, the G hat of x, and we compare whether this actually is the correct classification by looking at the true class G and the predicted class G hat and looking into this loss matrix to see what the associated loss is. And if the two classes coincide, the loss will be 0. And if they do not coincide, the loss for this matrix entry will be different from 0 and it will be positive. So some loss will be incurred. We describe this for all the different classes. So for all the different classes that we can expect seeing a particular object, we look at the expected loss incurred when we go over all the data distribution. Now, what we want to do is we want to minimize the prediction error. And that, of course, means we want to produce a classification such that our prediction becomes the one that minimizes this error. And minimizing means, of course, that the loss should be as small as possible. And here it's described, especially for the 0-1 loss case, as 1 minus the probability that I see a particular class. So I want to have a prediction that looks at that predicts the class that has the highest chance of appearing for a particular object. And of course, instead of looking at a predictor that minimizes this 1 minus the probability, I could as well describe my classifier as the one that picks the most probable class given a particular object description. Now, this is actually then the base classifier. So assuming that we know the true distribution, we know how often an object is classified with which probability into a particular class, we want to pick as a prediction the class that is most probable. And that's directly understandable from this loss matrix. Now, of course, there are two things particularly noteworthy here. First, this base classifier is an ideal case assuming complete knowledge. And usually when we learn something, we don't have complete knowledge. All that we do is we see data and we react on this data. So this is an idealized situation which is never occurs in practice. Okay, idealized situation. That's one thing. Then the other thing you might wonder, why, if we see a particular object, do we actually observe more than one particular class? Well, this is of course because when we see an object, that object is never described to the fullest extent. What we see is always an abstraction of the object. We see a few attributes, right? And of course, we could try to predict what you study just based on attributes like your shoe size, your height, your weight, whatever. And of course, these would not be very good attributes for describing what you study. And therefore, the probability that we would pick the right class here, even if we have perfect information about these attributes, is not very good. And it turns out, of course, that even if we have attributes that are highly predictive, there is still a chance that just based on these attributes, a different class might apply. And we will see an example for that, how this comes into game. So these are the two underlying assumptions here that may not be directly visible when you just read the text. So let's look at such an optimal Bayes classifier. Let's look at a scenario to make this a bit more transparent to you. So we assume here that we know how two different classes, a yellow class and a blue class, generate data instances. And what we assume here is that we have a bivariate Gaussian distribution. And from this bivariate Gaussian distribution, we generate 10 means, MK. And all these different mean values are labeled to belong to the class blue. Then we do the same and label them orange. And then what we do for both classes, we generate 100 samples. First, let's say for a class yellow, for example, we pick one of the 10 mean values, and then we generate with a smaller variation instances around this particular picked mean. So, for example, you see here the picture. And in this picture, for every dot here, we see whether it was produced from the blue distribution, so whether it belongs to one of the 10 normal distributions around the 10 means that belongs to the blue class, or whether it belongs to the yellow class. And what you see by this generation procedure, of course, is that there are no sharp distinctive line between these different data samples. And that's very natural, even if we have data about something and want to classify that data. Now, the optimal classifier, as we defined it on the previous slides, would always look at what is the probability that a particular point was produced by the yellow distribution or by the blue distribution. In this scenario, we know exactly where the 10 means for the 10 normal distributions of the yellow class and where the 10 means for the normal distribution for the blue class are. And therefore, we can estimate whether it's more probable that a dot comes from the yellow class than whether it comes from the blue class. But when we make this assignment, we may still do mistakes. And you see that, for example, here is a yellow dot in a very large blue neighborhood. So this yellow here means that it was originally produced by the yellow distribution and not by the blue one. But whatever kind of classifier we learn here, it will end up in the blue region because it just appears to be somewhat of an outlier of the yellow distribution. Now, here, with all this information given, we can actually produce the perfect delineation between these two classes. And even with such a perfect delineation where we always estimate precisely what is the probability that a point comes from the yellow or the blue distribution, and we know this very best, there is a chance that such a kind of an outlier arises in this other region where the probability for the other color, other class is much higher. So the optimal Bayes classifier gives us this very accurate picture. Now, this optimal Bayes classifier is the very best loss that we could produce. But in real data set, we will never know what the true underlying distributions are. Therefore, we will never achieve this perfect picture. And even if we would achieve it and we would see new data coming in, we would do mistakes. We would falsely classify this dot and this dot and this dot and this dot. And of course, also this dot and this dot. Now, what we can do is we can and we will learn about different classifiers. We have already learned about nearest neighbors. So this would be a 15 nearest neighbors approach. And this would separate the very same data set that we see here on the left into two regions, a yellow one and a blue one. And you see that we misclassify, of course, data points like this one or this one or this one or this one. And the picture would look different for 1 and n. This would generate different regions. And what we will do next is we will look at linear separability. And again, we will have here decision boundaries. And of course, we will do mistakes. So in general, we do not know what is the best strategy, actually, how to create our classifier from the data. Remember, optimal Bayes classifier assumes knowledge that we in practice never have. And even if we would have the very best solution, this optimal Bayes classifier, even then this would not be error-free. Okay, so what we have learned now is when we classify, we do mistakes, even under the best circumstances, and we incur a loss. Now, what are methods to optimize such kind of loss in a systematic way? We have seen KNN, of course, already. We have seen Bayes classifier, but can we also work more directly with this loss function? So let's look at logistic regression as a classification mechanism. And it's a regression task, so it suggests that we predict some numbers, but in the end, we turn the numbers we predict into probabilities for something belonging to one of several classes. And the idea of logistic regression is that we learn the weights similar as we do in linear regression. And to do this, what we try to mimic is the distribution of probabilities. We try to learn how probable it is that an object belongs to one class or the other class. And probabilities come always between the values of 0 and 1. So we try to predict probabilities that lie in this interval between 0 and 1. And what we will use in order to do this is this logistic function, this sigmoid function we will use. And this logistic function goes from 0 as we approach minus infinity. Then there is a rather small region around 0 where it increases strongly, and then it levels off at a value close to 1 as we approach plus infinity. How do we now add learning? Well, the idea is that we don't learn this function in general. All that we do is we learn a linear component of this function. This linear component is the same as in linear regression. Namely, it's a vector x transposed times beta, where beta again is a weight vector and x is our vector describing our object. And if we take this linear component into the exponential function, then this gives us a value. Now we want to make sure that we always predict values between 0 and 1. So what we do is we divide this by 1 plus this exponential function of x transpose beta. Now let us do a quick check. What happens if this linear component becomes very large? Then of course e to this power of this linear component becomes even larger, but the denominator grows as quickly as the numerator, actually grows even a tiny bit faster because 1 is added. So this term here, as we grow the linear component, is always a little bit larger in the denominator than in the numerator, but as we go against infinity, this term approaches 1. If the linear component here is negative, then e to the power of a negative number becomes a very small number. The same is true for this term here in the denominator. Then we have a very small number. This very small number here in the denominator can be neglected, and we divide by 1 plus a small number, so basically by 1. So we have a small number divided by something slightly larger than 1, so we have a very small number. So as the linear component up here goes against minus infinity, this overall term will go against 0 because e to the power of a very small negative number, like minus 1 million, of course, approaches 0 very quickly. So we map our linear component using the logistic function onto this term, and by this way ensure that our predicted values fall in the interval from 0 to 1. And this is what we then use to predict these probabilities. Now, when we have two classes, so we want to predict that our object falls into class 1 or that our object falls into class 2, we of course want to ensure that in these two class examples, the two probabilities add up to 1. Now, I have explained to you how this term behaves. And now in order to have, and of course the first constraint on a probability distribution is already fulfilled, namely that the term is between 0 and 1. Now we also want that the probabilities for the two classes add up to 1. Now we can simply look at what is missing, what kind of probability mass is missing, such that whatever linear component we have here, the other class gets the remaining probability mass. Well, but that's just 1 minus this term, and 1 minus this term is nothing else than 1 divided by this linear component plus 1. So when we express this in the diagram, the probability of the class being the first one is described by this black line. And as the probability for this black line increases, the second term describes the second class. The probability for the second class decreases. And the sum of these two functions always adds up exactly to 1. Obviously, I mean, you just add up this term, and then you have the same term in the numerator and in the denominator. Okay, so we have now a way to describe probabilities for classifying an object into one of two classes, and we have functions that fall into such that allow us to describe probabilities, and what we actually have to learn is only this beta. Now, this term can also be converted. So what we have now, we can look at the probability for one class, and the remainder probability is the other class. And the rationale between the probability and 1 minus the probability is also called the odds of an event. And the logarithm of this is also called the log odds or the logits. So when we describe the logits, then we take the logarithm of the one probability divided by the other probability. And if we fill in our functions that we used on the previous slide, we have these corresponding two terms. Now the denominators, they cancel each other out, and we get the logarithm of e to the power x transpose beta, and the logarithm of e to the power something is the same as x transpose beta. So the logits that describe the logarithm of the odds that an event happens is just described by this linear component, and that's the component that for which we want to learn the beta weights. The decision boundary now, so when is the nominator larger than the denominator or vice versa? This, of course, happens exactly when the logarithm is 0 or when this term overall is 1. So when the logarithm is 0, that's where this linear term switches from the one class prediction to the predicting the other class. So the boundaries where the logodds or logits are 0, this is all those x's where x transpose beta equals 0. We can also generalize this to several cases, several classes. Here's a multi-class case. Before I showed you the function in two-dimensional space. Now, of course, we get a higher dimensional space for describing that. How do we do this? This is now slightly differently, but not very much. So we have data. We have x's describing our objects, and we have our class descriptions. And for every class, we can say, or for every label, we say it falls into class 1 or class 2 or class 3 or class k. So what we now do for each of these possible values, 1, 2, 3, 4, until k, what we do is we provide a different column. We do a one-hot encoding in the indicator matrix Y. So we learn one weight vector for Y equals 1, another weight vector for Y equals 2, and so on and so forth. So we learn k many different separate weight vectors. And of course, what we can also do, instead of x, we can also have an arbitrary phi of x, yeah? But you can also just x transposed or phi of x transposed. So this is a feature function, just the same way that with feature functions in the linear regression case. So overall, this gives us then e to the power f of xy in the simplest case, just x transpose beta, divided by, and now we do this for all the different classes. Before we only had 2 classes. And so the remaining probability mass was always clear. Here we have to make sure that when we sum over all the different classes, all the different possible y values, we end up with a mass distribution or probability mass distribution of exactly 1. And by normalizing over the values that are produced by this f, that's what we get exactly. Of course, this also means that if we look at the odds of x belonging to the one class y or x belonging to another class z, and we then take the logarithm of that, again, the denominators will cancel out because they are exactly the same, and the odds are described exactly by the difference between f of xy and f of xz. So one's the class y and one's the class z. Now, again, having this data, what is the likelihood of a model? What is a model? A model basically is something where we have fixed the weight vector. And our data comes with descriptions of our x's and our y's. And now what is the probability that we see this data once we have fixed our weight vector? Well, we go through all the data points. We have n many data points. And we basically say the probability of producing one data point times the second probability producing the second data point times the probability producing the third, and so on until the nth data point. This is the probability that this weight vector produces exactly our data set. So we then look at how probable is it that we produce a data point. Well, we simply look at, given our weight vector beta, what is the probability that our xi produces our yi that we have observed in our training data. And we want to optimize this probability. This probability should be as high as possible. We had before the trick with the Bayesian classifier, already a naive Bayes classifier, that we said instead of multiplying these small probabilities, we rather take the logarithm of this term and then we sum over all our data points the logarithm of this probability. Well, so we turn the product into a sum of logarithms. And this is also called the log likelihood, the logarithm of the likelihood that the seen data was produced by a data distribution specified in this parametric manner. So we sum over all the data points and compute the logarithm of producing exactly the specific class as given in the training data for this specific object appearing in the training data. Now for the multi-class case, again, remember we have k-many different classes. For each column of our indicator matrix, we choose a corresponding weight vector and then define conditional class probabilities. So that's what I've showed you before. And now what we do is we want to have a loss which is optimal. And what we also do, not only is the loss basically encoded here in this probability, I should have maybe added the beta as influencing this probability. But what we also do is we regularize this log likelihood. And we regularize it in the very same way as we did for linear regression. We want to have small weights. So we square the weight vector and we have a regularization parameter lambda where we can say how important is it to us that the weights are small. Now, we can modify this instead of having this neg log likelihood. And one way to look at this is to think about it in the following way. When we have the observation that our ith data point encodes the classes in a specific way, namely in the way of a one-hot vector. What is a one-hot vector? A one-hot vector is 0 in all its different components. Only one single component is different from 0, and this is 1. And when I have many different classes, but I want to express that the ith data point, for example, has a category of 4, then in the 4th position of this vector, I would put the 1, and in all other positions, I would put the 0. You could say that's a verbose way of writing it, but it's a very useful way to conceptualize it, even if you don't want to implement it that way. Okay, so we have a one-hot vector describing that the ith data point, for example, in the 4th position, has a 1 describing that this data point has a category of 4 that should be predicted. And one way to describe this also is to say that the set component of this yi is exactly the test whether yi equals set. So if yi equals 4, we would have a 1 here, but if yi equals 1, for example, it would be a 0 because that would not be true. Now we can do a small notational trick. as before, we go over all data points, but now we add a sum that goes over all the possible classes. Remember, we have k many different classes. And for each class, we read out the value of this y bar I comma z. Now, this yi looks like this. And that means for all positions other than the correct prediction, we read out a 0. So we read out k many different entries, but actually only one of these entries is different from 0. So only one will have a 1 here, and all the others will make the rest meaningless. Okay, so we have a 1 here, and we take the logarithm that this object, or the logarithm of the probability that this object is classified into class Z. Now we have here the same set here and the same set here. But here we have a probability that belongs to our logistic regression. And here we have a distribution, which is a 1-0-1 distribution of values, which comes from our annotated data, which comes from our labeled training data. So this is our empirical observation, and this is what our model gives us. And we have two distributions. We have a distribution here, and we have a distribution here. And when we look at this precisely, then this is nothing else, this whole term, one distribution and another distribution, than the cross entropy between the one distribution and the other distribution. So this is the Greek letter eta for entropy, and the entropy between two distributions is the cross entropy. It's defined as the negative over all possible values of such a distribution, p of z logarithm q of z, where q and p are both different distributions, both in this case two multinomial probability distributions. Multinomial means you can have probabilities for k many different values. The loss that we get here is exactly the same as the neck-lock likelihood that we had before. However, we have now a large amount of freedom. The large amount of freedom comes from the fact that when we write this distribution here, we assumed it was exactly consisting of such one-hot vectors, and it works for such one-hot vectors. But we could also go away from this one-hot encoding. And one trick that we also will encounter later is that we say, okay, if we have annotated training data, we are not always sure that our labeling is always correct. So maybe we don't want to say that we are 100% sure that the category is, for example, category 4. And we rather want to say that there is a 0.99 probability that it's category 4, and all the other entries have a very small but non-zero probability that they could also be the correct categories for an object that is labeled. And actually, this is also done, as we will also see later in neural network descriptions, in order to avoid overfitting on particular data observations. And it can again be captured very nicely with the very same formula of cross entropy, describing this nice loss function. And indeed, cross entropy is one of the most used loss functions. So then, of course, we may also want to regularize it. So only then, when we have regularized the neck-lock likelihood before, we also put this into the picture and therefore regularize the cross entropy between the empirically observed distribution and the distribution that we encode with our model. And we add a punishment in the form of punishing large weight vectors. Now, what does this mean for two classes where we do the same approach? Well, for two classes, we always have the one class that has a certain probability, and then the other class has 1 minus this probability. So we have a little bit a simpler expression. We don't sum from 1 to k, but we just have class number 1 here, class number 2 here. We have a certain probability that our model predicts. This is this one here. And we have the remaining probability that our model predicts as described here. And this term can now be simplified to be this term, the linear component times the probability that is described in our label data set minus the logarithm of 1 plus e x transpose beta. Now, can we analytically solve this? Well, we would have to set the derivation to 0. Let's do the derivation of this part, and we want to set it to 0 as we wiggle the weight vector beta. We want to find the weight vector such that this cross entropy is optimal. And we go over all our data points, and of course we would have to derive according to beta. That's very simple for this first component. Simply the beta disappears. That's neat. For the second term here, deriving according to beta leads to this much more complicated term. And this more complicated term then eventually is the same as xi transpose, which we have in the first and the second term, and yi minus f hat of xi beta. So we look at what was the label minus what do we predict. But we have to do this times our object description, and we have to do it for all our objects, and we want to set this to 0. Now, unfortunately, there is no analytical solution for that, but we can take this term and try to find a 0 position by the iterative Newton method, where we update our beta, taking some random guess initially, and then increasingly approach lower values using Newton's method. And here, this is just the logarithm of the probability that I showed you on the slide before. And here we have to derive yet another time. There are variations of this approach, more about such gradient descent and some iterative solving later when we talk about neural networks. So, unfortunately, there is no analytical solution, but we can numerically look for such an optimal value of our beta. And the logistic regression is a nice function, so we have nice behavior and can actually find such an optimum. And this concludes this first part of this online lecture, and this also closes the logistic regression part.